All right. We're going to finish up this last module on electricity. We've talked about, last time we talked about different types of current, um, DC or AC, direct current or alternating current. Before that, we talked about Ohm's law. So we've been sort of building up to this final piece, which is just electric circuits. So if you think back many lectures ago, we started from just talking about charges on individual particles like electrons and protons. And then we've built our way up to talking about how they move, how they interact with each other. And we're going to end on actually how all this comes together and makes electric circuits. So any path along which electrons can flow is a circuit. Um, for a continuous flow of electrons, there must be a complete circuit with no gaps. So a gap would be any sort of break in a wire, or even a break within a component itself, like if you had a lamp and a filament in the lamp, like a bulb, and that filament burns out, well, that's an open circuit. So as long as that filament's there, you're going to have a complete circuit. If it's broken, so complete circuit versus open circuit. If it's broken, you're going to have an open circuit. Ideally, if we do have a gap in the circuit, it's because we want it to be there, which is usually where we like put a switch, because a switch can be opened or closed, and that's how we essentially, when you turn on a light switch on your wall, you're completing a circuit or breaking a circuit, depending on if you want the light on or off. So ideally, if there's a gap in the circuit, it's because we want it to be there. Of course, most circuits in the real world are more complicated than what we're going to talk about here. But circuits can have more than one device that receives electricity. And you can connect multiple devices in two different ways. You can connect them in series or parallel. And these are the two main types of circuits that you'll see if you're out and about looking at circuit boards inside your phone, or if you're looking at a wiring schematic for your house or something like that. These are the two main things you can break down those complex circuits into, is a series or parallel circuit. Um, in series, the components form a single pathway between the terminals of the battery and generator. Basically, everything's connected one at a time. In a parallel circuit, you could actually have multiple branches between the terminals of the battery. So we'll talk about these two things in detail here. So in a series circuit, all devices are connected end to end, and they form one path for the electron. So you can see here, I don't know which side is positive and which side is negative, but because it doesn't matter, we can actually draw the electron flow either direction. That's the cool thing with the way electricity is set up. We can actually draw from positive, negative, or negative to positive. The electrons actually flow in one direction, but when we analyze a circuit, we can actually go either direction and it works out. So let's say we go this way. Okay, so you can see we have a switch, so there's a gap in the circuit that's going to turn these lights on or off. But you'll notice if we take our pen and draw around here the whole circuit, it turns out that we only draw one path. We don't have to like lift up our pen and draw another one or anything like that. And we don't do multiple laps around the circuit. So this is a series circuit. There's one path. I just traced it for the electrons to flow. As soon as we turn this switch on and complete the circuit, pretty much the same current exists in all the devices. So like in this first light, we have some current I. In the second light, we have some current I. It's the same thing. Same thing here. The same current goes through everything. They all share the same value. Of course, if we increase the current, like in the case of the lamps here, if we increase the current, that means the lamps will actually get brighter. Of course, a break anywhere in this path, like where the switch is, will result in an open circuit. And that's going to stop that flow of electrons. So the important characteristics of these series connections, and this may get a little tricky, so I will go slow. Electric current only has one pathway. We just talked about that. So that is a feature to be aware of. If any of these devices fail, so if you take out one lamp, the whole thing breaks. And that's the bad thing about series circuits. If one component breaks, the whole circuit stops. So you can imagine the old Christmas lights. Back in the day, it was just a string of lights you put on your tree. And if one bulb burned out, you had to go through and check each one to see which one burned out. Oops. So the total resistance to the current in the circuit. So the resistance in the circuit. Oh, I'm still on eraser. There we go. So the total resistance in the circuit is the sum of the individual resistances. Okay, so everything in a series circuit is going to provide some resistance. For example, here, these light bulbs, they supply resistance. That's why they heat up and glow. So this first one should be an R1. This first light bulb has a resistance. This second light bulb has a different resistance. Like this could be, I don't know, 10 ohms. This one could be 12 ohms of resistance. This one could be 15 ohms of resistance. They could all have different resistances. But the point here is that the total resistance of the circuit, so the R subtotal is just R1 plus R2 plus R3. For a series circuit, you add everything up. Don't forget that the current is also the same no matter what. All of these have the same amount of electrons flowing through. So that means if we wanted to talk about the voltage, what we can do is just say that the current in the circuit, I for all of them, is numerically equal to the voltage supplied by the source, so the battery, voltage supplied by the battery, divided by the total resistance of the circuit, R total. Okay? So when you think about calculating the resistance of a series circuit, you have to add up all those individual pieces. And then you can think about applying that voltage to one big resistor. So the voltage across, or the voltage drop across each device, so the voltage drop, that means we're going to lose a little bit of the voltage over each device, is actually proportional to resistance. So Ohm's law applies here as well. So the whole point of this is that for the first light bulb, if we wanted to calculate the voltage drop across it, since they have different resistances, there'll be a different, if we look at the diagram, since they have different resistances, there'll be a different voltage drop, a different potential across each of these light bulbs, right? Because each one has different properties, so they're going to have different drops across them. If we wanted to calculate that voltage drop, so we can call it V1, because the first lamp is going to have a certain drop that's going to be different than the others. Okay, now we know the current is going to be the same for all of these, so it's just I, it's not I1. So it's going to be the current times the resistance of the first lamp. So in this case, 10 ohms. So if the current was like 1 amp, then we know we'd have a voltage drop of 10 volts. Same thing, we could move to the second lamp in this. It's going to have a separate voltage drop, but it has its own resistance. The third lamp is going to have its own voltage drop because it also has its own resistance. And it turns out when you add up these individual voltage drops, V1 plus V2 plus V3, you get the original voltage of your battery. So that means whatever is here, this big voltage in the battery that I'm labeling, big V, that gets broken up and divided among everything in that circuit. Now, parallel circuits are more common to see out in the wild, but their math is a little more tricky. So we'll have to be careful here. So in a parallel circuit, electrical devices are essentially connected directly to the same 2 points of the circuit. And essentially what that means is right here, we've got points A and B. You'll notice that B is just an extension of one of the battery terminals. So really, all three of these individual paths are just connected here to one battery terminal. Same thing over here. We have all three of these meeting up in one point, three different sort of smaller nested circuits. But if you look at where point A is connected, they're all tied into one terminal in the battery. So really, we can just think of A and B as the terminals on the battery. We could write this as the plus and minus on this side, but remember, because when we analyze the circuit, we can go either way, we could just as easily, if we wanted to, change that to negative and positive. Remember, that doesn't mean that electrons are flowing both directions. Electrons only have one true direction flow. It's just, I'm reiterating that we can do a circuit analysis in any direction we want to. So now that we know these are in parallel, what does that mean? Because clearly, if one of these light bulbs goes out or stops working, as you can see here, this light bulb has there's an open path because the switch is open. That light bulb turned off, but the other ones still actually burn. So why is that? And that is essentially because if we trace the path of our current here, I'll do it in green. We trace the path of our current, even though it can't go through this switch, it has other options. The electrons can't flow this way, so they're going to flow and complete the loops that they can. The complete circuits are going to flow that way. So even though one of these loops is broken, there's still two other viable paths, and the electrons are going to follow those paths. So that's a key feature of a parallel circuit is a break in one path does not interrupt the flow of charge in other paths. So the fact that you don't have to turn on all the lights in your house to use your toaster means that you have parallel circuits in your house. If everything in your house was on one series circuit, you'd have to have everything turned on to be able to use one thing. You'd have to turn on all the lights in your bathroom to like use your hair dryer. That would be a series circuit in a home, which would be a terrible idea. As far as important characteristics of parallel circuits, so each device connects the same 2 points, A and B of the circuit, right? So we see that here. And then the voltage is the same across each device. So this is where it's different. Remember with the series circuits, each loop gets no. In the series circuit, each device, those three original lamps, we have lamp 1, lamp 2, lamp 3. You'll remember that each one of these has a different voltage drop. Each one has a different voltage applied. And that's for the series circuit. But here, remember, all three of these lamps, lamp 1, lamp 2, lamp 3, they're all connected essentially straight to the terminals of the battery. We said earlier that A and B are essentially just extensions of the battery's terminals. So they all three pretty much have a direct connection to the battery. Okay, and because of that, the voltage is the same for all three of these. So last time the current was the same in series, now the voltage is the same. So no matter what you do, you're going to have the same voltage drop across all three of these lamps. So the current divides among the parallel branches, which makes sense, right? Each one of these lights has a different resistance. Oops, that should be R1, R2, R3. Each one of these lamps has different resistance, but the same voltage. Now, if we have the same voltage and we change the resistance each time, well, that means the current is going to change each time. So this one is going to have, I don't know, maybe lots of electrons flowing through it, while this one doesn't have hardly any. And then this one has no electrons flowing through it because it's broken. It's got its open switch. So here we see that we can actually use the voltage as sort of like an anchor point, right? We know V for all three of these. Now we can start looking at the different individual resistances and different currents flowing through these circuits. So we can actually apply Ohm's law to each branch of this parallel circuit. Now the total current has to equal when you add up the current through each circuit, each parallel piece, that added up equals the total current through the whole thing. So that means the total current, total equals first current plus the second current plus the third current. Okay. Now, here's something else to think about. As the number of branches is increased, you might think that that would also increase the resistance, but it actually works the opposite way. So here we have 3 branches, but if we increase that number, let's say something ridiculous, like if we had 100 branches, 100 lights stretched across this, the overall resistance is lowered. Okay, so the more lamps we put in here in parallel, we're going to have less and less resistance. And the question is why? Now, if you think about it in terms of hallways. If you are trying to get across campus and you have only one walkway, like a series circuit that's broken, you can't get across campus. Well, maybe if where you're trying to get to has 2 possible paths, if one of them's cut, you still have one other option, but there's still some resistance there. You're forced to take the only other option. Now, if you had 100 paths, so like 100 branches through the circuit, you have hardly any resistance at all. If you lose 1 or 2 or 10 of those paths, you still have 99, 98, or 90 more to pick from. There's so many paths, there's essentially no resistance, and cutting one of those doesn't affect your plans to move across campus. It's the same thing here. So the overall resistance of the circuit is less than any one particular branch, right? So if you have a really big resistance on one branch, doesn't matter. You've got all this current spread out over so many more. The resistance overall is going to drop drastically. So it's just the idea of sort of convenience for electrons. The more convenient it is for them to flow, the less resistance they're going to have. So if you had 100 paths, it would be so easy. But this is a bit of a counterintuitive point here. If we had, so here we have R1, R2, R3, we have let's think about it this way. We have R1, R2, R3, three different resistances. And what's crazy is the total resistance is less than all three of these, right? So whatever R1 is, our total is going to be less. Whatever R2 is, our total is going to be less. Whatever R3 is, our total is going to be less. So it is very strange. We can have some really big resistances in individual branches, but when we look at the resistance of the overall circuit, it's actually pretty small. And that is literally just from thinking about it as like a convenience factor for electrons to move. They may have three hard to use paths, but at the end of the day, they still have three paths. So that's going to make it easier than trying to just go through one giant resistor in series. But if you add too many, that can cause a problem. Obviously, lights and wall outlets are connected in parallel, so they all have the same 120 volt potential that's going to drive current through them. So here's just a schematic of your home appliances, and we know that there's going to be 120 volts potential difference. So as we keep adding things, so we've added a lamp, a heater, a toaster. As we turn more and more of these things on, we get more and more paths, right? So we have this first loop through the lamp. We have a second loop through the heater. Then we have a third loop through the toaster. So the more devices we plug in and turn on, the more pathways there are for current. So this is going to keep making it more convenient for current to flow. Therefore, the total resistance, the big resistance of this whole thing, is going to drop. So our total is going to go down. Now, what happens is if the total resistance becomes too small, then we're going to have overloading. Basically, wires can become so hot from overloading. They're able to move so much current through so many paths that essentially they can actually start a fire. And this is how a lot of electrical fires start, is just from having too many things plugged up. The wires get hot and melt. And that's where you get electrical fires from. Fortunately, we have fuses and circuit breakers. And the whole idea of a fuse, you can let me switch to a different color. Here we go, in black. Essentially, a fuse is a switch that's closed until it hits a particular amount of current. So, for example, if this was like to be maxed out at 20 amps, so this would be a 20 amp fuse. 20 amp fuse. As soon as enough current hits 20 amps flowing through it, it just snaps, it burns apart, and essentially it opens the circuit so no current can flow. And it's important that you put a fuse in series. So when it breaks, it turns off everything. And you can see here from my diagram, although it is a little cluttered, I can try to erase it. There we go. You can see from the diagram here, although there are things, the toaster, the heater, the lamp, there are things that are in parallel. All the current has to flow through this fuse first. So it's in series. And that's exactly where you want to fuse. When it breaks, you want the whole thing to be shut down. Fortunately, we don't have to use fuses anymore. So normally, if we had a 20 amp fuse and we suddenly pulled 20 amps of current, it would break and it would essentially fry the inside, just like a bulb being blown. Fortunately, we have circuit breakers now. And instead of having to replace a fuse, you just go down in your basement or wherever and flip that circuit breaker back over, and then it's good as new. So that's if you hear someone talking about a circuit breaker, it's literally the same thing as a fuse. And the diagram looks just like this here on the right. And again, the whole point of that was for times when like wires heat up and the insulation erodes. If that happens and two wires touch, that reduces the resistance in the circuit and it causes a short. And a short is essentially when two wires touch and there's not enough resistance between them. And then all of this is just for electrical safety in like homes and devices. I'm trying to think. Most like even hair dryers. So if we had a hair dryer, or if you go with the heater, so even the heater in this circuit here will probably also have a fuse in here. So not only do most appliances provide their own fuses, you also have circuit breakers in your home, so you're sort of doubly protected. Okay, so with that being said, that's essentially finished everything I wanted to talk about for electricity. Next, we will move to magnetism. So that's got this finished up. Hopefully this was short. Definitely look through the book, the textbook. There's lots of everyday examples from this section. And you can sort of get a better idea of where you'll see these things from in everyday life.